Good evening, friends. Welcome back to this is day 10, right? The chemical bonding 10th day, right? Where we are going to discuss about yes, Ganesh, Anna. Good evening, right? We are going to discuss about the valence shell electron pair repulsion theory, or we call as VSEPR, which is proposed by Sedgwick and Powell in 1940 and Gillespie and Nyholm in 1957. This is improved because of some shortcomings. What is the concept of that? Already we discussed that your as the number of atoms are combining more and more in covalent bonding, where more than two elements are undergoing the combination. So there, how many valence electron or lone pair bonded pair electrons present within the central atom? This is going to play a very vital role to decide the structure of the molecule. So our Lewis concept of covalent bonding, or which we call as the electronic theory of valency, this has failed to explain. This has failed to explain why molecules have different structure. It also failed to explain about the bond length and bond energy. That's why this theory was developed. This theory was developed, which is called valence shell electron pair repulsion theory, or we call it as a VSEPR. VSEPR. According to this theory, what it is saying? It is saying that because lone pair of electron, it is only attracted towards the nucleus, or there is no other attraction. Lone pair has only attraction towards the central nucleus, whereas bonded pair electron, it is attracted between the nucleus, means central nucleus, as well as the surrounding nucleus also. So, as a lone pair electron present within the central atom, so this gives the different shape because of repulsion. So what? Now lone pair can repel the lone pair because both are electrons. Lone pair can repel the bonded pair. The lone pair, in other words, the electrons which are present in the valence shell but not participating in the bond formation, we call as a lone pair. Whereas bonded pair of electron is saying that these are the valence shell electron present within the valence shell and participated in the bond formation. So between lone pair and lone pair, there can be repulsion. Between lone pair and bond pair, there also can be repulsion. There also can be repulsion. And between bonded pair also there could be a repulsion. And it is practically observed that lone pair has a more repulsion than lone pair bonded pair repulsion, and it is greater than bond pair repulsion. What is the reason? The reason here, lone pair only attached to the central atom, whereas the bond pair electron is attached to central atom as well as the surrounding atom. That is the reason. That's why here attraction or here repulsion is a little bit less. Attraction is more. Here, no attraction at all, only attraction to the central atom. That's why lone pair repulsion is greater than lone pair bond pair repulsion is greater than bond pair repulsion. Because, yes, tell me. Okay. So that's why lone pair will occupy more space because of repulsion. That's why whenever the structure we are predicting, if we know about how many lone pairs are present, how many bonded pairs are present, we can prescribe the or we can predict the shape of the molecule or structure of the molecule. Right. So this we call as valence electron pair repulsion theory. So here valence repel. That's why it is called a repulsion theory, which is mainly used for predicting the size or shape of the molecule. So in our previous case, we discussed already, right? Whatever case one we discussed, case one we discussed, if the central molecule or central atom has two bonded pair or four bonded pair with a zero lone pair, zero lone pair means no lone pair, the molecule shape of the molecule will be linear. The shape of the molecule is linear with bond angle will be how much? 180 degree. 180 degree. So this is your case one. Like this is happening in case of your DCl2, carbon dioxide, hydrogen cyanide case. This is case one. Okay. Coming to the case two. Case two, we discussed in our last class also. Right. In case two, if there is a three bonded pair of electron with a zero lone pair with a central atom. Right. So here the shape will be trigonal, or we call trigonal planar. Trigonal planar with bond angle will be how much? Now 120 degree. Right. Which is happening in case of boron trifluoride. Next, sulfur dioxide, sulfur dioxide. These are the examples. These are the examples. Case 3. Case what? The 3 we discussed already. Under case 3, what we discussed? If it has a four bonded pair, it has a four bonded pair with a zero lone pair. Zero lone pair of electrons. So here the structure will be tetrahedral. What it is? A tetrahedral with a bond angle will be how much? Now near about 109 degree, 28 minutes. 28 minutes. The example we have taken, that is a methane gas. What gas? Methane gas. Where the bond angle is how much? 109 degree, 28 minutes. So up to this we have discussed up to case 3. Now let's take the case 4. So case 4. So under case 4, we are going to discuss if there is a lone pair. If there is a lone pair. So let us consider there are three bonded pair is present along with one lone pair electron is present with the central atom. Then what will be the structure? What will be the structure? So let us take the case of, for this, let us take a case of ammonia, NH3. So how ammonia is formed? So you can say the nitrogen plus three hydrogen reacting with your two NH3 or ammonia. So here nitrogen and hydrogen both are non-metals. Both are what? Non-metals. So the primary requirement for the covalent bonding, it is fully filled. It is fully filled. So ammonia is formed by covalent bonding. It is formed by covalent bonding. So nitrogen, first point about the nitrogen, the atomic number is a 7. The electronic configuration we can write helium configuration, that is 2 over, and the rest your 5 means 2s2, 2p3. So it has how many electrons in the outermost? You can observe here. So here there is a pair of electron here, and there are three unpaired electron. Three unpaired electron with the nitrogen. So that's why these three electron it will share with three hydrogen. It will share with three hydrogen. Right. Okay. So next is a hydrogen. The atomic number is 1. Electronic configuration is 1s1. So it has an unpaired electron in s orbital. So that's why what will happen here? Now one nitrogen will share three hydrogen. This is one nitrogen. So it will share one electron here, and there will be these two electrons. So three, it is sharing with the three hydrogen. So this is another hydrogen. Right. So it will form three bonds with the three surrounding hydrogen. And these two electrons are the lone pair. These two electrons are what? The lone pair. So there is a lone pair of electron with the nitrogen, with the nitrogen which is nothing but the central atom, which is nothing but the central atom. So here this lone pair, what it will do? Because of this presence of lone pair, so it is expected to form this tetrahedral structure. Okay, it is expected because it is similar to CH4. It is similar to CH4, so it is expected to form tetrahedral structure. But presence of this lone pair of electron, presence of this lone pair of electron, what it will do? That this lone pair will repel this bond pair of electron. It will repel this bond pair of electron, so that this structure will convert like this. Because of repulsion, what will happen? Then a nitrogen will be at the central place with a pair of a pair of lone electron. This will repel the bond pair. So one nitrogen will bond here with the one hydrogen, and backside there will be second nitrogen here. So this is the second hydrogen, right? And this is the third hydrogen. So this is one electron, this is second electron, this is third electron, right? So your this because of this repulsion, your lone pair repel the bonded pair of electron, repel the bonded pair of electron, because of which this bond angle will decrease. The bond angle will decrease because your lone pair repulsion is greater than bond pair. So this lone pair will repel this bond pair more than the bond pair with a bond pair with a bond pair. That's why the bond angle will decrease to 107 degree. To how much degree? 107 degree, 48 minutes. So further it will decrease because in recent years we have observed that instead of being 90 degree, it become 109 degree 28 minutes because of bond pair they repel each other. So in case of CH4 we observed already. Now this is the C, one is hydrogen here, second hydrogen here, third hydrogen here, fourth hydrogen here. So these all are bonded pair of electron, bonded pair of electron. Right. Okay. So there are four bonded pair, but no lone pair. So what will happen? Now these bonded pair, they will repel each other. They will repel each other because of this repulsion. Because of this repulsion, the bond pair or this bond will shift. So it will organize in an angle manner. So this will convert into what? Now like this. So carbon will be central atom, one hydrogen will be top, right? And second hydrogen on the three sides or three corner you can say, right? So this is another hydrogen, this is third hydrogen. With bond angle is how much degree here? Because of this repulsion. Because of this repulsion, the bond angle will be equal to 109 degree 28 minutes. So here bond pair repulsion is occurring. Remember here bond pair repulsion is occurring, but in this case the lone pair repulsion is occurring as well as bond pair repulsion is occurring. So here lone pair repulsion is greater than the bond pair repulsion. That's why the angle further decreasing. The angle is further decreasing and forming a shape. This shape is called what shape you observe here, right? The shape is like this. This is called trigonal pyramidal. What is this shape called? The trigonal pyramidal. Whereas this shape is called tetrahedral. This shape is called the tetrahedral. So like this shape. Right. So like this shape, this we call as a tetrahedral shape, whereas this we call as trigonal pyramidal. Trigonal pyramidal shape with the bond angle is how much? 107 degree 48 minutes. So this is a case number 4. Case number 4. That with a three bonded pair with a one lone pair of electron. Then the shape will be here triagonal pyramidal diagonal pyramidal shape with bond angle will be 107 degree your 48 minutes. 48 minutes. This is your case 4. Case 4. Right. Coming to the case 5. Coming to the case 5. Right. So in case 5, if there are two bonded pair and two lone pair, two bonded pair and two lone pair, then what will be the shape? What will be the shape? Right. Oh, case 4. Case 5. Case 5. If there are two bonded pair with two lone pair, means two electrons are shared, right? Two pair of electrons are shared, and two electrons are a lone pair. So, like in case of water, the example of this one is a water molecule. So, how the water is forming? Now, you can say hydrogen reacting with oxygen, and it is forming 2H2O. 2H2O. That means both are non-metals. So that means it is forming by covalent bond. It is forming by covalent bond. So first is your oxygen.
Yeah.
Because what happened? Lakshmi,
Adele.
Lakshmi, mute yourself. Okay. So oxygen is a central atom. Oxygen is a central atom. Atomic number is how much? 8. The electronic configuration is your helium configuration, 2 electron over, next 2s2, 2p4. So it is this is a completely filled and the p orbital is a partially filled with 2 electron here and there are 2 unpaired electron in 2py and 2pz. So this is a 2py1 and 2pz the 1. So it has a 2 electron unpaired electron. That's why it will share with 2 hydrogen. It will share with 2 hydrogen. So hydrogen atomic number is 1. The electronic configuration is 1s1. So it has a 1 unpaired electron in s orbital. So that's why your central atom will be oxygen. So oxygen. So what it will do? It will share 1 electron with a 1 hydrogen. So this is a 1. So this is a 1 hydrogen. Right. And this is the second hydrogen. Right. So it is sharing. And remaining, how many pair of electrons remaining you see here? This is 1, this is another. Means there are 2 lone pairs are left here with the central atom. With the central atom. Right. So presence of this lone pair, what it will do? Now this lone pair, it will repel the bond pair. It will repel the bond pair of electron. Right. That's right. The angle will be disturbed here. So what will happen? Already I told the lone pair, it will occupy the more space around the central atom. The shape will be like this. And this is oxygen. This is one lone pair. And this is the second lone pair. Right. And this is one hydrogen. And this is second hydrogen with a bond pair. With what? A bond pair of electron. So these lone pair will occupy more space. So they repel each other. They repel each other. So there is a force of repulsion there. And this also repel this bond pair of electron. This also repels the bond pair of electron, and the bond pair repulsion is less here because lone pair repulsion is more than bond pair repulsion is more than bond pair repulsion. That means this repulsion is more than this repulsion, than this repulsion. So that's why the bond angle further decrease. The bond angle further decrease to how much degree? Now this will be equal to 104 degree, your 31 minutes. 31 minutes because of these three conditions. What are the three conditions? Lone pair repulsion is greater than bond pair repulsion is greater than bond pair repulsion. So here there are two lone pairs are there. So they repel more and they will occupy more space. They will occupy more space. This lone pair, what they will do? They will repel this bond pair further. Right. So they will repel here. And bond pair repulsion, it is just decreasing. It is a decreasing. That's why the bond angle is decreasing to 104 degree. So this is your case 5. This is your case 5 is saying that if there is a two bond pair with a two lone pair of electron with the central atom, the shape will be V shape. The shape will be V shape with a bond angle will be how much? 104 degree, your 31 minutes. The example is your, so this example is nothing but your water. And case for example is your water. Case for example is ammonia NH3. Right. So like that, you can predict the shape of the molecule. You can predict the shape of the molecule if you know the your how many lone pair electrons are present, how many bonded pair of electrons present with the central atom. Right. So these are the 5 cases we observed. 5 cases we observed, and there are some more cases also there in intermediate. You'll study more and more about this. But this is the main 5 cases, right? Now, if there are two bond pair or four bonded pair with a no lone pair, the shape will be linear in shape, with bond angle will be your 180 degree in order to have the minimum repulsion, so that combined energy will be less, right? Second one example of this is your BeCl2, carbon dioxide, hydrogen cyanide. Case 2. If there are three bonded pair of electrons with a zero lone pair, means no lone pair, the shape will be trigonal planar shape with bond angle will be how much? Your 120 degree because of bond pair repulsion. Bond pair repulsion, which is happening like in case of boron trichloride, sulfur dioxide. Okay, case 3. If there are four bonded pair with a no lone pair or zero lone pair, right? Which is happening in case of methane gas. Which is happening in case of methane gas. So here, four bonded pair are there, so they will repel each other. That's why the structure becomes tetrahedral structure. The structure becomes tetrahedral, with a bond angle will be how much? 109 degree 28 minutes. Means like this. Four hydrogen will be like this. One hydrogen will be up. Right. So that's what we call as a tetrahedral structure. Okay. Coming to the fourth one. If there are three bonded pair with a one lone pair, so there is a lone pair bond pair repulsion, which will be greater than bond pair repulsion. So it is expected to be tetrahedral structure. But because of presence of lone pair, which repel the bond pair more than the bond pair repulsion, that's why the structure will be what? The trigonal pyramidal shape with a bond angle will decrease to 107 degree 48 minutes. Okay. Coming to the case number 5. If there are two bonded pair with a two lone pair, two bonded pair with a two lone pair, so here what will happen? The lone pair repulsion will be greater than the bond pair repulsion will be greater than the bond pair repulsion. So this lone pair will repel more and it will occupy more space around the central atom, and they will repel the bonded pair. They will repel the bonded pair, right? As the repel the bonded pair, what happens? Now this bond will shift. This bond will move in this direction. This bond will move in this direction, right? Because between this bonded pair, repulsion is less. So this repulsion is more, then this repulsion, then this repulsion. That's why the shape of the water molecule is a V shape with a bond angle further little decrease, that is equal to 104 degree 30 watt minute. So this theory we call as valence shell electron pair repulsion theory, which is proposed by Civic and Powell in 1940 and improved by Gillespie and Nyholm in 1957, which is generally used for predicting the structure of the molecule. Structure of the molecule. Right. Now you can observe here, still this theory, which is put forward by Sidwick and Powell or Gillespie and Nyholm, still you observe here, this theory still it is believing in, still it is believing in the Lewis concept of a covalent bonding. Lewis concept of covalent bonding. Here it is saying that both hydrogen and oxygen are non-metal. That's a covalent bonding is forming. Means it is depending on right. So still it is depending on the Lewis theory of covalent bonding. Lewis theory of covalent bonding. That's why it could not explain. It could not explain about the bond energy, bond strength. It could not explain. It could not explain about bond length, bond energy, and electronic nature of a certain covalent compound. Electronic nature means like water molecule, polar covalent bond, like a polar covalent bond. The electronic nature of the covalent bonding, it could not explain, but it explained only about the structure of the molecule. Structure of the molecule. If we know how many lone pairs are present, how many bonded pair of electrons present with the central atom. It only predicted the nature or shape of the structure of the molecule. So rest of the things are remain uh, undisclosed, undisclosed, or rest of the thing like bond length, bond energy, and electronic nature of the covalent bonding. It could not explain. It could not explain. Moreover, if we talk, because this is a 1957, so by 1957, orbitals development already occurred, right? So by the year 1957, we are in the modern theory. We are in the modern theory, and modern theory is saying that an atom not only consists of orbit, it consists of suborbit. It consists of suborbit and orbital. Suborbit and orbital. So when the two atoms are coming close, their orbits are going to be overlap or not? Their orbits are going to be overlap. And orbit consists of suborbit. Means the suborbit also going to overlap. It is also going to overlap. Right. When the suborbit or subshell is going to overlap, subshell or suborbit consists of orbital, according to our quantum mechanical model of atom. Quantum mechanical model of atom. So according to quantum mechanical model, it is saying that every orbit consists of a suborbit and orbital. So when the two atoms are coming close, their orbits are going to overlap. Their orbits are going to overlap. So if orbits are going to overlap, orbit consists of orbital. Orbit consists of orbital. Why orbitals are not overlapping? Why orbitals are not overlapping? So this is called the quantum aspect of chemical bonding. Quantum aspect of a chemical bonding, or this chemical bonding based on the quantum mechanical model. This is proposed by Linus Pauling. This is proposed by Linus Pauling. in 1954. In 1954, he proposed another theory which we call as Valence bond theory. So this theory, what we call it, Valence bond theory. Bond theory, which explain about your quantum mechanical model based on quantum mechanical model. Means based on orbitals. Based on what you can say, the based on orbitals. Based on orbitals. Right. That's right. This theory also called as orbital overlapping theory. Orbital overlapping theory. It is also called as valence bond theory, or it is also called as orbital overlapping theory, which was put forward by Linus Pauling. Linus Pauling, who invented the electronegativity scale. Who invented the electronegativity scale in 1954. 1954. So this theory was developed by Linus Pauling in order to explain about the quantum aspect of the chemical bonding. So how the orbitals are overlapping? Because an orbit can consist of an orbit can consist of your variety type of orbital. What are they? Now, S, P, D, and F. So there are four orbitals are present because we don't know about the F orbital. Step of F orbital till now it is not known. So remaining SPD, remaining what the SPD of one atom can overlap with the second atom, with the second atom of same SPD. You know, so there can be a overlapping between S with S or S with P, right? Or S with D or P with S or S with P, same only. So this is the common. This is the common. Next, P with P. P with what the P. Or P with D. P with what the D. Or D with S. That is common. And D with D. D with what the D. So there are several type of overlapping may possible. So here in this lesson we are going to discuss only three type of overlapping. What are they? The first overlapping we are going to discuss that is called SS overlapping. The second one we are going to discuss that is called SP overlapping. And the third one we are going to discuss about PP overlapping. So here we are going to discuss only about three type of overlapping. One is SS overlapping, one is SP overlapping, third one is PP overlapping under this theory. Rest of the overlapping you will study in your intermediate second year. Right. So, what is this SS overlapping? Just I'm giving a gist because time is left. Okay, very few time is there, just 2 minutes there. SS overlapping means S orbital of one atom that overlap with another S orbital of another atom. This is called SS overlapping. Similarly, S orbital of one atom that overlap with P orbital of another atom that is called SP overlapping. Right. Then coming to the third one, it is called PP overlapping. Means P orbital of one element, it overlap with the P orbitals of other element. Right. These three type of overlapping, it gives the structure or it gives a new theory that we call as hybridization. We call as a hybridization, which is our last theory about the chemical bonding. So from this is very important. Remember that the next class will be very important in order to understand the hybridization. In order to understand the hybridization, next class is very important, and you have to understand about SS overlapping, SP overlapping, and PP overlapping with their shape of the orbital. Shape of the orbital. Very interesting concept is there here, right? Okay.